let's say that we have an inductor with inductance L and a capacitor, capacitance C in a circuit like this. So we have an LC circuit. And at some moment in time, the charge on the capacitor is Q star. And the maximum charge on the capacitor is capital Q, let's say. But we are, at some moment in time, in a situation where the charge on the capacitor is Q star, not the maximum value. And when that is the value of the charge on the capacitor, say we want to know what is the current in the circuit, or the current in the inductor. So there are two ways of going about this. The hard way is going through time, and in the same way that if I ask for the speed of an object at some height after it's launched from some other height, I don't have to go through time. I can just use energy conservation. The same is true here, but let's just go through both ways to notice how much more complicated it is if we go through time. So the equation for the current is minus, well, maybe we should start with, let's start with the charge, because we've been given some values for the charge, and then we can get the current from a time derivative. So the charge is the maximum amplitude, the amplitude, which is the maximum value of the charge, say, times the cosine of omega t, and omega is 1 over the square root of LC, plus phi, but let's assume that phi is 0. So, right, phi is 0, the initial value of the charge at t equals 0 is the maximum value. We can just scale that. And what we need is the time to find the current, which is the derivative of this. So that's going to be a sine or minus. We're going to bring in 1 over the square root of LC. So we get sine of t over LC square root. And what we need here is t. Right, so that's what we need to find to be able to get the current at the moment when the charge on the capacitor is Q star. But what that means is that Q, we go through this equation, that has to reduce to Q star. And so the only unknown here is t, and so we can get t. So t from this, we'll get the t, and then we'll plug it into here. T is, we do Q star over big Q, and then we have to do the inverse cosine of that to isolate this term, then multiply by the square root of LC. So t becomes the square root of LC times the inverse cosine of Q star over Q. So we can now plug this in. I becomes minus capital Q over LC sine of, let's open a square bracket, 1 over LC, this, times t, which is this, so that's the square root of LC times the inverse cosine of Q star over capital Q. And this simplifies to minus q over LC square root sine of inverse cosine of q star over capital Q. So we need to figure that out. But let's notice that, so let's say from, right, we know sine squared of x plus cosine squared x equals 1. So how do we do this? Sine squared of, what is the quantity we're looking for? The cosine to the minus 1 of q star over capital Q. So the sine squared of this plus the cosine squared of that this must equal to 1. And so the sine of the inverse cosine of q star over capital Q is equal to 1 minus the cosine squared of the inverse cosine of q star over capital Q square root. And so that just, these are the inverse of each other, so we get 1 minus q star over capital Q squared, square root, and so let's go to another sheet. We can write this as, and so our current I is equal to plus or minus capital Q over the square root of LC times the square root of 1 minus q star over Q, or capital Q squared, which we can write more succinctly as plus or minus square root of capital Q squared minus q star squared all over LC. And obviously that wasn't that easy. Okay, so we want to end up here in a much more straightforward way. And we can do that by avoiding going through time. So let's avoid going through time and let's use energy, conservation, energy conservation. Right, we know that the energy in the inductor, Li squared over 2, plus the energy in the capacitor, which is Q squared over 2C, is equal to the total energy. So in the capacitor, we are at some moment in time when we have Q star in the capacitor. So all of this is known. We're trying to find this. We know this. So the total energy must be known. But the total energy can be written in terms of the known maximum charge, which is capital Q squared over 2C. After all, at t equals 0, the capacitor is fully charged, and so the total energy in the LC circuit must be that. And so it's just a one-line expression, and we can solve for the current. What follows from that is simply, right, we're going to take this and bring it over here, multiply by 2, divide by L, and we'll end up at plus or minus the square root of, same thing as we have there, 1 over LC times capital Q squared minus Q star squared. So much more straightforward using energy conservation than going through time.